Hello everyone, my name is Ruben Hernández and I will present our work titled Generating Style-Based Palm-Vein Synthetic Images for the Creation of Large-Scale Datasets. This work was developed by Edwin Salazar and a research team with my supervision as part of the preliminary research of his PhD thesis in the PhD program in Applied Mathematics at the Universidad Católica del Maule and the Laboratory of Technological Research in Pattern Recognition. Individual recognition through their biometric traits is an essential component of modern society, both for civil and security purposes, with several applications such as e-government, healthcare, banking, among others. Biometric systems use physical and behavioral traits that must be unique to each individual while being universal and unchanging over time. However, the collection of biometric data for the creation of large databases for the validation of the proposed method is a challenging task in terms of cost and time. Furthermore, there is the difficulty of finding a large number of people willing to share their characteristics because concerns about privacy violations. Thus, the problem or question is how to collect biometric data for the creation of large databases. In the last decade, emerging and more robust biometrics techniques such as palm-vein patterns have started to gain presence over more widespread ones, for example, fingerprint. Particularly, palm-vein patterns have two distinct advantages. Vein can only be captured in living bodies, making non-presential fraud techniques very difficult to perform. And secondly, due to vein are internal living structures, they are very difficult to copy or fake and are not damaged by external factors. Comparing vein-based or vascular biometrics against other biometrics traits in the graph, it's noticed that finger and palm vein highlight by the difficulty of replication and acquiring the biometric data in daily life. Hence, palm vein recognition has been mainly used for computer device, access control, and others. Most of the proposed research use publicly available databases for the validation of its techniques. In spite of that, as we can see in the table, the available datasets are very limited and have a small number of subjects, which limits to conduct the scalability test on large-scale databases, simulating real-world application of massive identification. When a system is evaluated on a large number of individuals, in the order of hundreds of thousands or millions, a minimal error can be equivalent to a high number of erroneous results. Besides, it's very important to verify how the system is able to handle a large volume of queries or the time required to process a query in a large database. Despite the above, and due to the limitation of current databases, only a small number of works have studied the performance of their proposals in large databases of vein patterns. In image processing, synthetic images are very useful to validate the performance of the proposed algorithms, especially in biometric. This is a controversial topic with pros and cons. Although this kind of image should not replace in its entirely the validation with real images, synthetic biometrics are very useful in many cases. For example, for fingerprints recognition, face recognition, iris, identification, or signature. The synthetic generation of biometric samples facilitates the validation of the robustness of biometric systems with thousands of subjects. From the state of the art, there are some contributions that have attempted to simulate or generate images of veins. However, to the best of our knowledge, there is not any to generate synthetic pal vein images. From the reported papers, we can divide them into two main categories. The first group is represented by three approaches which are based on the structure of vessels. It is worth to mention that vein patterns usually present unpredictable structures, angles, and complicated trajectories. In addition, vessels are hidden under skin, varying their depth. Therefore, classical structure-based models fails for generating realistic-looking images. Thus, in the second category, texture-based approaches use generalist models to simulate the visual and texture properties of vein patterns images. Among them, with the emerging and growing of generative adversarial networks, GAN-based approaches have been proposed with the main purpose of increasing the number of samples in the databases. Based on the previous results, the high complexity of vessel structure and the ability of GANs to encode visual information on image details and texture, in our proposed approach, we explore the generation of synthetic pal vein images by using a GAN-based model. Contrary to former GAN-based methods, we take advantage of GANs to produce realistic and unique pal vein images that simulate individual samples for creating a large-scale database by using image augmentation. Pal vein recognition systems capture images using near-infrared illumination. The acquisition process produces images with very particular characteristics in terms of texture, illumination, and contrast. Hence, in this work, we introduce a new model based on a GAN model for generating synthetic pal vein images for the creation for large-scale database. Thus, our main contributions are a new method to increase the number of region of interest samples, a novel specific domain application for the style-based GAN architecture, and the largest dataset of pal vein images of the state of the art, comprised of 10,000 subjects with 6 samples per each. Our proposed approach is represented in the figure, and it is based on the STAL-GAN2 model. Firstly, since GANs require a large number of training data and the number of samples of public datasets is limited, we implemented a procedure to increase the number of ROI samples. Different from other approaches that apply image augmentation from the ROI samples, we increase the samples by moving and rotating a central sliding window within the entire PAL ROI. Secondly, we use the STAL-GAN2 model by using the 850 band of Kezia dataset as the training subset. The training subset was originally comprised of 1,200 pal vein images, and after performing the procedure of ROI samples augmentation, we obtained more than 100,000 training images. Later, it is important to ensure that new images generated by the vein image generator are unique to be part of a biometric database. Thus, we implemented a uniqueness discriminator that takes each new image generated and compares it against all images in the synthetic database. The discriminator uses a similarity score calculated based on our method previously proposed for palm recognition and establishing a uniqueness threshold equal to 0.1. The final step of our method aims to increase the number of samples from the generated images, which correspond to different individuals in on the datasets. This process is important in order to generate a biometric database composed of several samples for each individual. For this purpose, we consider the natural transformation that occur during the acquisition process of palm images using non-contact device. For example, blurring variations, contrast, and lighting, and those produced by the location of the hand on the device, I mean translation and rotation. Therefore, by applying random combination of this visual transformation on the generated image, we obtain several samples. So we conducted extensive evaluation of the synthetic images to measure their visual quality and relevance, comparing to real images of publicly available datasets. Then the proposed dataset is the largest of the state of the art, being 20 times larger in the number of individuals and 10 times larger in the total number of samples compared with the biggest one now, the PolyU dataset. Moreover, it is worth mentioning that since the process of creating the synthetic database is incremental, it is feasible to continue increasing the number of individuals that compose it. Since the number of samples in our database is much higher than the available reference data, for the comparison in all experiments, we consider only the 10% of the individual in our database by comparing one sample per subject against the same number of samples from each dataset, all of them taken randomly. Then first we evaluate the visual similarity between synthetic images and publicly datasets, and later we evaluate the same datasets by using quantitative metrics. The experiments were conducted on a dedicated server consisting of these hardware and software settings. In order to analyze the texture similarity between generated and real images, we use one second order texture, the gray level co-occurrence matrix, and one higher order statistics, the deep image structure and texture similarity index. In the top figures depicts the plots obtained for each reference dataset comparing to our generated synthetic database. We show the obtained scatter plots for the GLCM dissimilarity and correlation, where the covariance confidence ellipse are also represented. It's noticeable that there is a significant overlap between both data distribution except for the PUT database, and this result can be attributed to the fact that palm imaging systems are not standardized. The second row in the figure presents the color representation of the distance matrix computed by using this index. It's worth noting that for no reference dataset, these values exceed 0.5, and their mean values are close to 0.3, which evidences high texture similarities between the compared datasets. Aiming to quantitatively measure the similarity of the distribution between real and generated images, we use three metrics in the feature space that is more robust than the pixel space for measuring the similarity. With this proposal, we compute the FID for evaluating the statistics of two subsets of synthetic and real images. The accuracy based on one nearest neighbor classifier to predict labels of real and generated images. And thereby, we can estimate the similarity of both datasets by the accuracy of a leave one out scheme. And contrary to classical classification problems, in this case, the closer the value is to 50%, the more similar the two datasets are supposed to be, since the classifier misclassifies them. In order to complement the evaluation, we finally assess both distributions by computing recall and precision metrics to quantify how much of the synthetic data can be generated by a part of the real distribution and vice versa. The table summarizes the results of the quantitative measuring between real and generated images. And again, for the quantitative metrics, the put dataset shows results that evidence its dissimilarity from the generated dataset. However, in general terms, the experimental results show that the realism of the obtained Palbane images is acceptable compared to the reference datasets. Finally, we conclude that the proposed model is able to generate synthetic Palbane images of unique individual for the creation of large-scale datasets. The image generator produces images with the same realistic characteristics as real images in terms of texture, illumination, and contrast. And also, the obtained dataset is the largest of the state-of-the-art, which is only a first version, since we will continue to increasing the number of individuals. Besides, as future work, we plan to evaluate other generative models, such as different GAN architecture or BQ model, with the aim of coding more complex characteristics related to Palbane patterns. So this is our work, hoping you all can download, use, and share the datasets. Thank you for your attention. And now we are able to answer any question.